Many good notebooks exist on probability and mathematical statistics written at the undergraduate level. This notebook aims to deal with the theory of both probability and statistical inference for undergraduate students in statistics or other areas in which a good understanding of statistical concepts is essential. The note includes the core materials that are usually taught in a one-semester sequence. The prerequisite is 1 year's worth of calculus. That should be enough to understand a major portion of the note. There are sections for which some familiarity with combinatorics, limit theory, derivation, integration, multiple integration, and partial differentiation will be beneficial. The first two chapters introduce the basic concepts and techniques in probability theory, including the calculus of probability, conditional probability, independence of events, Bayes' theorem. The next three chapters contain the concepts of the random variables, probability distributions, transformations, expectation, moment, the most important, discrete continuous distributions, and the properties of these concepts. Chapter 6 develops the notions of multivariate random variables or random vectors, independence of random variables, conditional distributions, conditional expectation, and the basic concepts of random simulation. Chapter 7 contains some mixed areas, standard probability inequalities, law of large numbers, and the central limit theorem. The remainder of the notes systematically develops the concepts of statistical inference. The sample statistics are defined in Chapter 8. This chapter contains the basic statistics and Glivenko's theorem. The point estimate, the confidence interval, the Cramer-Rao inequality, the method of moment estimator, maximum likelihood estimator are developed in Chapter 9. Two-sided alternative hypothesis, likelihood ratio, and chi-squared tests are developed in Chapter 10. Chapters 9 and 10 present the basic ideas of large sample confidence intervals and text procedures. Our main aim is the modeling of a random experiment. In the study of the subject of probability, we first imagine an appropriate random experiment. A random experiment has three important components, which are multiplicity of outcomes, uncertainty regarding the outcomes, and the repetition of the experiment in identical fashions. Suppose that one tosses a fair coin with faces head and tail. Let us assume that the tossed coin will land on either H, that is head, or T, that is tail. Every time one tosses the coin, there is the possibility of the coin landing on its head or tail. Multiplicity of outcomes. But no one can say with absolute certainty whether the coin would land on its head or, for that matter, on its tail. Uncertainty regarding the outcomes. One may toss this coin as many times as one likes under identical conditions, repetition, provided the coin is not damaged in any way in the process of tossing it successively. All three components are crucial ingredients of a random experiment. We interpret probability of an event as the relative frequency of the occurrence of that event in a number of independent and identical replications of the experiment. We may be curious to know the magnitude of the probability P of observing the ahead H when a particular coin is tossed. In order to gather valuable information about P, we may decide to toss the coin 10 times for example, and suppose that the following sequence of head and tail is observed. Let K be the number of heads observed in a sequence of n tosses of the coin, while K over n refers to the associated relative frequency of the head. For the observed sequence, relative frequencies of the head is 4 over 10. The observed values for K over n empirically provide a sense of what P may be, but admittedly, this particular observed sequence of relative frequencies appears a little unstable. However, as the number of tosses increases, the oscillations between the successive values of K over n will become less noticeable, and ultimately K over n and P are expected to become indistinguishable in the sense that in the long haul, K over n will be very close to P. That is, our instinct may simply lead us to interpret P as the limit of K over n as n tends to infinity. The course is attended by a large number of undergraduate and graduate students with diverse backgrounds. Accordingly, we have tried to strike a balance between simplicity in exposition and sophistication in analytical reasoning. Some of the more mathematically rigorous analysis has been just sketched or intuitively explained in the test so that complex proofs do not stand in the way of an otherwise simple exposition. This note is suitable for students and practicing engineers who need a quick reference to any probability distribution or table. It is also useful for self-study where a number of careful solved examples. This course entitled Numerical Methods and Optimization, number 2, is jointly set up by Dr. Attila Hazi and myself, Dr. Agbeko Kwami. We are both from the Institute of Mathematics at University of Miskolc.